Hi, welcome to the Signal Path. In this episode, I have another product review for you guys. We'll be taking a look at the QuantAsylum QA403, which is a 24-bit audio analyzer. Now, this thing has extraordinary performance. I mean, over 120 dB of total harmonic distortion. It has 2-channel generators and 2-channel analyzers, all differential, and it can be cascaded with some of the other products they make through the expansion connector. Fully USB powered, a USB interface with its own software that runs on the computer, which we will take a detailed look at. The reason this caught my attention was because we were measuring the Stanford Research ultra-low distortion generator. And in order to measure its total harmonic distortion, I had to go through all the bunch of trouble building filters and so on to be able to do that. And this can measure it raw, which is really impressive. So at first we want to take it apart, take a look inside and see how it is built, why is it as linear as it is, and what kind of component it uses, and then a bunch of experiments to evaluate its performance. So let's get started. And taking the top cover off reveals a single PCB solution for the entire instrument. On the left we have all the digital stuff, and on the right all the good analog circuitry clearly separated into sections, and a fairly interesting looking light pipe that brings all the LEDs to the front panel of the unit. Now, I think that there is a lot to talk about here, especially on how they preserve the dynamic range and the linearity of the analog circuits on the right, and what components they use to bring the signals in and out of the ADC and DAC, and of course the digital section here and how it transfers power over. So I think let's take a close look at it. Now, this is a 4-channel instrument. We have 2 input channels over here, and we have 2 output channels from here and from here. Now, in a way, the design of the input is very similar to an oscilloscope, except that this instrument is processing everything differentially. The input can be both differential or single-ended. If you want to use it single-ended, you just have to terminate the other one into a short, which means that the entire information in the front end has to be preserved differentially all the way to the ADC at the end of the chain. Now, this is quite difficult to do because, first of all, you have to be ready for both of those conditions, but you also have to preserve the noise and the linearity of the ADC as much as possible while being able to accommodate a very, very large input range of signals, because you don't know what the user is going to connect to the ADCs, of course. Now on the DAC, we have a similar issue. The signals coming from the DAC also have to end up differentially on 2 channels. Now on the DAC side, if you're not using 1 channel, it's okay, you just basically leave it floating. But in the ADC side, you do have to short it. So I want to take a look and see how they've accomplished this, how they've gone through different blocks and what kind of components they're using between the input terminals and the ADC. So let's go backwards and take a look at the specification of the ADC itself. Now, both the ADC and the DAC over here, they are both 32-bit architectures, and they're by ESS. Now, I have the primary specification of the ADC over here, and you look at this performance, it's extraordinary. This is basically the world's best audio ADC that you can get your hand on. 125 dB of dynamic range, 118 dB of THD plus noise, and of course the THD by itself is even better than that, and it has 2 channels. And you can see it doesn't make too much of a difference whether you use it in mono or dual channel. When you turn 2 channels on, there's crosstalks and so on within the same piece of semiconductor that this is built in, so it's quite difficult to accomplish the isolation. These are very, very, very small numbers. Now, the interface to this is not very fast because we're not dealing with a lot of data at the end of the day, and the instrument is going to run this at 192 kilosample per second with some promise of potentially double that in some future firmware updates, at least for the ADC itself. Now, the internal architecture of the ADC at the chip level is quite abstracted here. You can see we have 2 ADC cores right here and here. Each of them are going to need a differential input, of course, and each of them have a low noise regulator connected to them. This is very common, especially for high dynamic range data converters, so that you can have as much power supply rejection ratio as possible. Note how there are 2 completely different regulators. They're not shared, so that you cannot have noise coupling back into them. And then there's this massive digital core that sits behind the ADC. And this is because in audio applications, a lot of times you want to have filters, FIR and IIR filters, and all kind of manipulations of the digital data in hardware before you pass it on to the next stage of whatever the sound system that you may be dealing with. And they put that directly on the die in order to make sure that you can have this hardware availability to do all this manipulation of the data without having to rely on software later, which is great. And I have 1 chain of that signal flow actually here, and you can see that from the ADC data, we do have things like distortion compensations, IRR filters, quite a few of them at multiple sample rates. We do have gain adjustments and digital FIR filters and so on and on. And this is all very obviously for audio applications. Now, I'm not sure how much of this is used in this particular instrument for the application it is being used for in this case, but nonetheless, these are available and can be manipulated. And that's all great, and that gives us these 4 inputs basically. So we have our ADC over here, and then if we go backwards, we have to now worry about how do we connect these 2 inputs directly to the ADC. So if we go from the 2 differential inputs, we do have a pair of op amps over here that are used. I'm going to show you those, and then there is a actual relay in here, and these relays allow you to switch the front end into different actual attenuation values. And this is pretty important because this thing can take a very large input signal swing, and you have to attenuate it quite a bit before you even fit it to the first op amp, because then the input of the op amp nonlinearity will become dominant. So in the cases of high attenuation, you can set the attenuation with some mechanical attenuation over here, pass it through the op amp, and then there is some additional electronic attenuator solid state, and then some more op amps following it. So what do these op amps look like? Well, the very first set of op amps are themselves extremely linear. We're talking about distortions of 0.000015%. So extremely linear, actually quite a bit more linear than the ADC itself, which is to be expected. Very, very high open loop gain. And these things are, reasonably good noise. 1.1 nanovolts per square root hertz is pretty good at 1 kilohertz. And they support rail-to-rail outputs and inputs and so on, which is great. And if you look at its actual output amplitude and its own THD, which you can get from the datasheet, you can see that as the output level increases, the THD and noise gets better up to a certain point, and then it shoots up immediately afterwards. So here the op amp is noise limited, and here the op amp is distortion limited, and there's some sweet spot at where it produces the best signal. So they have to put themselves across this curve in the right places to be able to accommodate the front end. And here's a basic implementation front end of it. You can see that the input is actually a bipolar differential pair. So it's a fully bipolar implementation in this case. Now after that, we need to select some attenuation. And in that case, they have a bank of attenuation resistors here with a mux. And this is an analog mux with switches built in. That's why it's solid state, unlike this one, which uses a relay. And this allows you to adjust some of the further attenuations. And the combination of these two will give you a very large range of attenuations. And then after that, you have to prepare the signal for a differential input directly into the ADC. And for that, you're going to need another pair of op amps. So there's one over here, and there's one over here. And that's the last 2 stages before driving the actual ADC. And that's what these look like, fully differential ones. Again, the distortion is really, really good. Not as good as the original one, but it's pretty amazing, and it's better than the ADC anyway. And this is a differential and differential out. It itself also has a THD versus noise versus frequency plot that you see here, and as of course as the frequency gets higher and higher, you do get some THD and noise penalty. All of that is to be expected. So they have to take everything here into account and put these stages one after the other in order to be able to feed the final signal into the ADC with the best linearity and noise possible. And in a similar fashion, we do have our DAC over here, which also is responsible for generating a very high dynamic range signal, and they are followed by quite a few of these op amps as well in order to get the differential signal, do various gain stages and control the gain, control the output amplitude, and then select the total output attenuation using relays as well before it is fed to the 2 differential outputs, left and right channels basically. And the DAC itself is also 32-bit, extremely good performance. Just like the ADC, they're basically a pair together, intended to be used simultaneously in audio applications. Similarly, it has a big digital core in the front with things like FIR filters and volume control and the emphasis and PCM and so on. And then we do have the digital PLL here that control and run the clock of the DACs. And these are pretty important, just like ADCs. DACs also have to have an extremely low jitter digital PLL in order to produce very clean signals. Otherwise, it translates to a reduction of effective number of bits in exactly the same way. And then we do have our 2 outputs, SPI and I2C interface available, external crystals and so on, all are put together in order to make the DACs possible in a very similar way. If you look at on this board, we do have a very clean crystal that is built here that is split between the ADC and the DAC, so they can run coherently. So when you do a loopback, basically the frequency is exactly what you would expect, and the samples line up basically at exactly the same time intervals that you would expect. It's nice to have a single one. You get some correlation between the 2 of them. And then on the other side of this whole thing, we have the processor which interfaces with the USB. And you can clearly see a big cut here in the PCB, and this completely separates the 2 halves. So this entire section on the left is galvanically floating. So you don't have to have ground loops, and you can avoid that in some situations. At the same time, you have to make sure that you have taken care of your grounding reasonably well. Otherwise, you run into some other problems. Here's the light pipe we saw. There is an expansion port over here, which is capable of things like I2S, because they do make a whole bunch of other instruments that you can connect this to. These are transformers used to pass power into this left side of the circuit, because otherwise there's no way to give power to these. These are basically modulated on the right side and then rectified and regulated on the left side before they're fed to the individual components. And then we have some opto-isolators here for sending data like SPI back and forth and other control signals back and forth. And that makes the entire instrument. Now, one of the quickest way to find the boundary conditions of the performance of the unit is to do a loopback test, essentially use the instrument to measure itself. And that's exactly what I've done. I've connected the output of the DAC to the input of the ADCs. Now, we have two channels, so we can do this essentially twice. Now, I've also done this single-ended, meaning that I'm using only two of the inputs, one of the positive inputs of each of the ADCs, and the other two inputs are connected to some BNC shorts. And the other two outputs of the DACs are floating. This is in a way a tougher test for the instrument, because by making a single-ended measurement on each of the ADCs and the DACs, we cannot eliminate the second harmonic distortions, and you will see that in the measurement too. So this is going to give us some good idea, and it also gives us a chance to familiarize ourselves with the GUI. And here's the application that controls the instrument. It's a really lightweight executable. As a result, it's quite fast and is updated regularly to fix bugs and add features. Now, when you install this, there's also a really detailed help file that comes with the instrument. But on top of that, there's a wiki page that goes into the details of pretty much everything you would want to do with the instrument, including the APIs to control it with Python, Java, C++, or simple REST API for very basic control of it through some scripting. This is a lot of attention to details, and don't get fooled by the fact that this is a smaller company. They have really taken these things seriously. The GUI does report the USB voltage and current arriving at the instrument, which is pretty important in case you're connecting it to something that cannot deliver the appropriate current and voltage to it. This is a nice little touch there, and here it tells you that the REST server for the API is also running in the background. Now, all the buttons on the left side, if you hover over them, it tells you some information about what they do, why they're important, and how you can configure them. The instrument starts with the highest level of attenuation to be expected, so the input is as protected as possible, and we can adjust the sample rate here up to 192. So let's set to 192 kilosamples per second, and let's increase the number of FFTs to, let's say, 64,000. We change the number of FFTs, obviously it has to capture longer durations before you can compute that, so the number of frames you get is going to slow down. That's quite normal. Let's go ahead and run that. There we go. Now, as soon as you run this, you get your displayed average noise level for the particular number of FFTs that you have and for the sample rate that you have. Now, we're sitting at around minus 110 dB. That's because we have 42 dB of attenuation in the front of this. There's quite a bit of noise figure that we add to the system as a result of this. Now, we can go ahead and set the actual attenuation to 0, and that brings the noise all the way down to around minus 150. And we can also add averages. For example, let's say if I add 8 averages, there you go, that's what you see over here. And then we can add little markers on top of this to read that. But if I want to put down a marker like this by clicking on the waveform, it says markers can only be placed when only the left channel is active. I'm not sure why that is and why that limitation even has to be there. So if I need to turn off the right channel, and then I can put a marker here. At 80 hertz or so, it looks like it's triple the AC line coming in. So there's definitely some coupling into it, which is inevitable. Keep in mind these signals are tiny. Minus 139 dB volt is a really, really small signal. So we can go ahead and erase all of that. I'm going to enable the right channel at the same time, so they're fairly identical in terms of their displayed average noise level, which is what you would expect. Both of the DACs are turned off. There's nothing being applied there, and those DACs are controlled with the generator portion here, and the cursors are controlled here at the bottom. We also have an option of a few different kinds of windowing: Hanning, flat top, Blackman-Harris, Hamming, and of course the rectangular. Each of these windowing tops for FFTs have different pros and cons, which if you study any signal processing, you'd be familiar with. And they're used for various types of analysis depending on what is most important to you. So a flat top, for example, gives you really good amplitude accuracy, very low ripple in the passband. But if you really want other properties of it, such as spectral leakage from bin to bin of an FFT when you rectangularly window something, you may want to use a different windowing top. Here I've changed the sample rate to 96 kilosamples per second. Let's turn the right channel off and look at the generator. Let's right click here. You can set the settings of the generator here. I have 1 kilohertz and 0 dB volts, which is a reasonable amount. We can click OK and enable it. Now we get exactly what we expect. We're getting a 0 dB volt signal coming straight out of the generator. It's sitting where it should be. It's a nice clean tone. Now, we don't see any harmonics, and that's not surprising because the harmonics are so small that they're buried in the noise floor of this measurement currently because we have such a large input attenuation. Now, there's a strategy in optimizing the dynamic range of an instrument like this. You back away the attenuations until you see the best compromise between noise floor and nonlinearity. If the signal is too strong, the noise is going to be really good because you don't have attenuation, but then the nonlinearity is going to affect the ADC beyond its full-scale input or close to its full-scale input. So we can back it away and see what happens. 24 to 18. Do we see any harmonic? We're beginning to see a little bit of harmonic peak out, but we don't see any of the other ones. So we can back it away further. Here's 12. There we go. A few more are becoming visible here. So it's time to turn on the averaging to make sure that we're not missing anything. Let's put the averaging back to, let's say, 10 averages this time. And there it is. There are indeed some harmonics here now present. So let's put some markers on this. Here's the peak one. Here's the second harmonic, third harmonic, and there's no fourth one. And there's a fifth harmonic right over there. We can also pick this one too just for fun, all the way out there. And look at that. The fifth harmonic, which is the largest harmonic coming out here, is at minus 123 dB down. That's amazing. That's quite a linear system. Now I can put it down to 6 dB. Let's see if it gets any better than that. No, it doesn't get better. In fact, the third harmonic then becomes the dominant value over here. So somewhere between 6 and 12 is probably the nominal value. Let's leave it here at 12 again. Look at that. Wow, that's really impressive. Let's go ahead and turn on some automatic measurements. Now there's a lot of different measurements that you can apply, and I'll show you that. There's some of them that are built in for quick access, but if you right click over here, you can see all the different measurements you can apply, and that is extensive. So let's go down over here and select THD. Here's THD in dB and THD+N in dB, and we're applying it in the left channel. And we can apply exactly the same measurements on the right channel, and in fact they're both supported. So even though there are sometimes asymmetries in what you can do, in this case you can apply the measurements into both. Let's press OK over here. And look at that. THD minus 119 dB, and a THD+N minus 104 dB. These are excellent numbers. Let's go ahead and put it to 6 to see if things get any better. Let's look at the THD. No, it doesn't really get that much better. It was better before. So let's put it back on to 12. There we go. The THD+N gets a little bit worse with 12, but the overall compromise, I think, is worthwhile. So this is a really good number. Now we can also enable the right channel. And you'll notice right away that the right channel is a little bit worse than the left channel. The noise is a little bit lower, but certainly the nonlinearities are worse. I went ahead and I swapped the inputs, and then the nonlinearity swaps with it. This tells us that the nonlinearity is coming from the DAC and not from the ADC. And this is somewhat expected because of the semiconductor variations, and just matching from channel to channel, you're going to have a difference in performance between the two DAC channels. Now these numbers are so small that these differences are absolutely tiny in absolute volts, but they're nonetheless there. It would be nice if they were exactly the same, and you may get lucky if you purchase a unit, they may actually end up being the same. This is process variation in this case. Now we can go ahead and apply a cursor and see the differences between these, or we can just add the THD measurement and compare them. So if I right click over here, go down and put this one and this one, which is on the right channel, I get two other measurements, and you see that there's about a 6 dB of difference between these two channels. So 6 dB of THD difference. Now the THD+N of them isn't that different. You can in fact see the channel 3 is slightly better, and you can kind of see its noise is a little bit better, but that's just process variation again. Now at the bottom of here, we have some cursors that we can apply, and you can choose where to put the cursors on the left and on the right channel. So let's say I enable the first cursor over here. I can move it around by dragging it around. I wish these numbers were larger. They're super tiny. I think it would be good if they were, somewhere outside of the plot, perhaps a much larger font here at the bottom, as long as they're not overlapping the waveform. Let's bring this close to, let's say, the worst case situation, which is here, and then we can press peak, and it catches the highest value nearby. So it works reasonably well. And then we can enable the second channel too, and now it's sitting on the right channel. The color is red. Bring it all the way around here too, and say peak, and it jumps to the other one. Now the delta between them, you can see, for instance, that the third harmonic difference is about 7.5 dB between the two channels. That's just the imperfection and the variation. So these measurements can be done pretty quickly, which is nice. Now even if you disable the right channel, these measurements in the background actually continue. That's because the acquisition is done. It's just not simply displayed. Now, one of the other things you can do with this is that you can use the built-in visualizers. So for example, I can go into the DHD bar graph, and it shows you all the harmonics. As long as they're of course above the noise floor, they will be accurate. So the left channel's most dominant harmonics can come and go. You can see what they are. And if you add all these powers, and that's the number you're going to end up with, which is a THD at the top of the screen. You can also enable the right channel, but then unfortunately the numbers disappear. I wish the numbers were just vertically showing on top of these bars. And if you disable the left channels, the numbers completely disappear. So they're not treating the right channel as much again. They should be showing those numbers for both of the channels. A minor complaint. I'm sure they can easily fix that. Now, another visualizer that I really like that's built in, it's called residual display. And what that does is that it gives you a time domain response, but it does something clever in there. It applies an infinite impulse response right at the dominant tone. So it knows what the generator setting is, 1 kilohertz, and it basically mathematically completely nulls that out for you. So then if you zoom in and look at the waveform, the residual waveform is everything except the fundamental signal. And right now the THD is so good that the residual is just gibberish. It's 10 to the minus 6 volts anyway. But in case if you have a nonlinearity that's strong or a particular type of nonlinearity, the residual display left over in time can give you great insight in what that nonlinearity looks like and where to look for it in a system. So this can be quite handy in the cases of some strong nonlinearity or maybe even just some strong interference if you want to see what that waveform, for example, looks like, which is really nice. So just going to turn this off. Let's turn the right channel off for a second. Let's turn both of these off as well, so we're only looking at this waveform. Now we do have a second generator as well, so we can generate 2 tones pretty easily. We can also generate multi-tone, but let's right click on the second generator, and I have set it to 1.1 kilohertz, which means it's going to generate another tone just as strong, 0 dB volts, which is 100 kilohertz away from this. So as soon as I enable that, now I expect to see additional intermodulation terms appear in the spectrum as well. Let's go ahead and enable that. There we go. There is our second tone. And let's reset the averaging here so we can see everything clearly. There we go. Here's our intermodulation terms. I mean, look at these intermodulation terms. This is ridiculous. They're sitting so far down. It must be one of the most linear systems, certainly at this price point, that I've seen up to 20 kilohertz. Now all the other tones are mixing together. And guess what? We also have now the IM2 term, which is the difference between these two sitting at 100 hertz, also sitting at minus 121 dB. So all the imperfections of the front end can now be fully characterized and understood. If I turn the right channel on, we see a very similar IM2, but we do indeed see somewhat of a worse harmonic distortion there. So this hopefully gave you a good kind of an intuition of what we can do and how we can play around with the different settings of the instrument using the GUI itself. But now let's connect it to the Stanford Research generator and see if we can measure its THD raw and if it matches what we did in the previous video. So let's go ahead and verify the performance of our Stanford Research ultra-low distortion function generator, which I repaired in one of the previous videos. Now there I did not have access to this instrument here, so I measured the THD of this using a rather unique method, using a lock-in amplifier. But here we can measure it raw using this QuantAsylum digitizer. So I have the two outputs directly connected to a differential input on one of the channels of the digitizer there. The frequency is the same, 775 hertz, exactly like before, amplitude of 1.4 volt RMS differential between the two channels. So let's go and see if we can replicate our measurements from before. So here's what we're measuring when the output of our function generator is disabled. And there's a couple of tones that are there. These are actually coupling from the 60 hertz line and its harmonics into the instrument. Now the QuantAsylum is fully floating, but we saw that when we do a loopback, we don't see any of these. So this is being picked up from the environment by the Stanford Research, and there must be a way to get rid of it, but I could not find a way to completely eliminate them. It doesn't matter. For the purposes of the THD, we're still in the safe side. And just to prove to you, we can click on one of these, and you can see that it is indeed at 2 times 60 hertz, and these are all different harmonics of that. So let's get rid of this, and let's go ahead and enable our output. So here we go. There it is. Here's our waveform. And we can go ahead and enable the averaging as well. Now, one thing I wish they would do with the GUI is that if there was an enable and disable averaging, rather than having to click this up every time, if there is one, I couldn't find it, so that way you can basically have this count already and then just enable and disable it so you don't have to keep clicking multiple times. Now, the first thing to note, on top of everything else, is that we do have a lot of spectral leakage. And that's because we're at 775 hertz, and we're trying to sample that. And the two sources are completely not coherent. There is no way to lock the clock of the QuantAsylum to a different instrument. And that's one of the reasons why different windowing methods are available. I wish there was a way to lock them, but I understand that there are complications in the quality of that clock once you start to think about doing things like that. But so we see some leakage over there. So let's change that to a different kind of windowing. Let's try Blackman-Harris windowing here, which helps with the leakage quite significantly. Now we're averaging as well. Let's wait for the averaging to stop and take a look at this number. Minus 150.6 dB is the THD of this source. And when I measured it using a lock-in amplifier, I got minus 140.8. So essentially almost exactly the same as the measurement we're seeing here. That's really quite amazing that we can measure this raw. Remember, in my measurement, I had to put a null filter just to be able to make that measurement. And here we can see that the source is slightly even cleaner than that. So let's go ahead and characterize another Stanford Research Systems product here. This is the Model SR560, which is a low-noise preamplifier, a very highly sought-after instrument because of its noise and linearity performance and typically coupled as an input of a lock-in amplifier. This actually can be battery-operated to even lower its noise further, although I've plugged it into an AC line in this case. So it offers two inputs, A and B, and it can operate single-ended or take the difference between them. Here, of course, I'm operating a single-ended, so we have the generator's positive output in the left channel going into port A input of the SR560. And then we take the output of the SR560 and feed it into one of the channels of the detector here, the ADC. So basically, we can characterize all kinds of things about its response. It has a few features. It has a built-in low-pass and high-pass filter, and you can configure them with different cutoff frequencies with 6 or 12 dB per octave drop in them. So this makes it quite powerful because aside from making a high-pass or a low-pass, you can activate them both and make a bandpass filter. Very useful for getting rid of signals that you don't want. You can also control its gain anywhere from 1 volt per volt all the way to 5 times 10 to the 4 volts per volt. So a lot of gain. And of course, it will have effect on its linearity input and output. And then over here, we have another thing called the gain mode, which you can switch between a high dynamic reserve or low noise. Basically a compromise between a low noise floor or a high linearity. And we can characterize the difference between these with the QuantAsylum, which will be very cool because we can see exactly what the compromises are depending on how it is used. And here's the output of the SR560 with no input applied. Again, we're seeing the harmonics of the power line coming in. I do need some better filtering, it looks like, around the lab to get rid of this. It shows how polluted the power lines actually are in the lab. Now, I have not applied any signal, but I have set the SR560's gain to be 0 dB, so 1 volt per volt. So whatever I put at the input should come out of the output. If you look at the generator settings, I'm putting 1 kilohertz at minus 20 dB volt. If I go ahead and enable the generator, you can see that the output measurement is done at about 100 millivolt RMS, which is minus 20 dB volt, and the instrument can calculate the gain, which is essentially 0, just below 0. And here's the main tone coming out at a minus 20. And we can already see the second harmonic here present. So our THD is about minus 90 dB. And the THD+N is about the same value because it's dominated by the power of this. So in this situation, it's quite linear. Now, minus 90 is a lot worse than the internal instrument, so we're very confident with this measurement. But minus 90 is still pretty good. So let's go ahead and increase the amplitude here. Let's take the amplitude all the way to, let's say, 0. Now, with 0 dB volt at the input, we are getting 1 volt RMS also at the output, and the gain is still the same, but of course the THD is quite a bit worse. Now we're at minus 70. So it grew with the input, and that's because the input and output of this instrument are going to have some nonlinearity, and it produces all of these harmonics and many, many more of them going to the output. The QA403 has this additional function, which is a frequency response calculator built into it, and it does this by generating an exponential chirp and essentially monitoring the output. So it does a sweep and tells you what the gain of the circuit is. So let's turn the generator off here and look at the settings over here. So here's our stimulus, which is an exponential chirp. I'm sure they'll add more there in the future. There's only one right now. And you can set the amplitude, and that's important because you want to make sure you don't compress anything. Here I have set it to 0, and you can mute various portions of it and edit some additional chirp functions. Let's just leave it at default for now, 0 dB sweeping from what is almost DC to 20 kilohertz. Okay, let's go and enable that. And when I enable that, what do we get? We get a flat line. And that tells us that the SR560, when none of its filters are enabled, has a very flat frequency response from DC to 20 kilohertz. I can in fact enable one of these markers, and you can read the value, minus 0.07 dB volt. That's the gain basically. And look at that, completely flat, because the exponential chirp coming in is at 0 dB volt, and we know that it's linear at that point. So it's a very, very nice flat response. But we know it also has filters built in. So we can go ahead and enable one of the filters. So here you go. So this is now a 1 kilohertz low pass filter enabled with 6 dB per octave drop. and you can see nicely dropping there. We can calculate, or I should say measure, the 3 dB bandwidth. The 3 dB bandwidth is 957 Hertz for a 6 dB per octave. And if I change the slope to 12 dB per octave, you can see that the slope gets sharper and the 3 dB bandwidth certainly moves back. So now the 3 dB bandwidth of it can be measured around 616 Hertz or so. Then we can swap it and make it a high-pass filter at exactly the same cutoff. And here's a high-pass, also 6 dB per octave. We can increase the slope to 12 dB per octave. Works really nicely. And we can then combine the low-pass and the high-pass at the same cutoff frequency. Now we get a bandpass. Now in this situation, you can only run it at 6 dB per octave, and that's because they're essentially using the other stages in order to get the high pass and the low pass. There's only so many filters that are built in. And it works really, really nicely. I really like this feature of the SR560. We don't have to have the frequencies at the same point. I can make the bandpass larger. For example, I can increase the cutoff of the low pass filter to 10 kilohertz, and you can see now it is a broader response, and I can bring the high pass, for example, further back. But this is very helpful in rejecting noise that you don't want, and the SR560 does a really good job in that. So let's try and measure the gain of this circuit now and see if we can adjust the SR560's gain. I'm putting now a very small signal in, minus 60 dB volt, and it is coming out at minus 60 dB volt. The gain right now is 0. Let's increase the gain over here. Here is a 20 dB gain, and you can see it measures it perfectly, 20 dB gain, and the signal coming out is 20 dB larger than the input. We can keep increasing that. Here is now 40 dB. There it is. Looks pretty good. And look how the noise has also moved up, because the output noise power spectral density is also going to get worse and worse as you increase the gain of this. Okay, that looks good. Can I make it a little bit larger? Okay, it's 45 dB, here's 53, 54 dB of gain, and the noise continues to move up. Now, one of the nice things about this instrument is that you can use some of these automated tests to characterize instruments automatically. But there's one little thing I wanted to show you. Now, if I go into the visualizer and look at the residual display that we were looking at before, zoom in a bit more. Now this information is a little bit more useful. You can see that the residual display has an asymmetry between the highest and the lowest point of the input signal, and that's because of the way the input and output nonlinearities of the SR560 are actually operating. So this can be quite helpful when the nonlinearities are somewhat significant. Remember, this is still a very, very small signal, 10 to the minus 6 volts. So let's use some of the built-in automated tests of the QA403 in order to characterize the SR560's high dynamic range versus low noise mode that I talked about earlier. Now if you click on this, you see a lot of different things you can characterize, and it's really quite impressive because it can create multi-dimensional sweeps and give you all these plots that fully characterizes the device you want to measure. Now in this case, I'm interested in measuring the THD+N as a function of input and output power. So you're going to select that. It's automatic characterization of the amplifier, THD versus input and output. Now if you click on that, you get to configure it completely. So I want to go from minus 50 dB volts to minus 25 dB volt. SR560 is set to have 40 dB of gain, so at minus 25, that's producing quite a large signal. And then it's going to do 1 dB at a time. And I'm going to plot THD+N because I want to see both the noise and the nonlinearity effect that I'm comparing against. Now I'm going to call this series DR for high dynamic range. I have set the SR560 to be in the high dynamic range mode. Now as soon as you click OK, it's going to run that automatically for you, and it's going to set the appropriate attenuations to make sure that the instrument is not limiting you. And you can see up here that it is counting 1 dB at a time from the generator. And the gain is constant, and the noise is quite high because we have a 40 dB of gain. It's way, way higher than the instrument. Right now we see essentially no nonlinearity. So this is entirely limited by noise at the moment. So it's going to keep going for a while until it settles down to the minus 25 dB input. And here's our plot. Look at that. So it basically gets better and better and better up to a certain point, and then it shoots up. That's because here we are limited by noise, and the noise floor is constant. So the larger the output signal, but the better THD+N parameter becomes. But at some point, it's going to hit the linearity, and then the whole thing jumps up because it's going to be purely due to harmonics. Now look at all these harmonics. I mean, it's saturating the SR560. Now we can do this measurement again, keeping this where it is. Go back over here and do it one more time. This time I'm going to actually change the settings of the SR560. I'm going to put it into the low noise mode in that situation. So I've already changed that. We're going to change the series name now to LN. I'm going to run it one more time, and it's going to do exactly the same thing and make a similar plot. And here it is, look at that. There is a significant difference between the two. In the high dynamic range, the THD+N is worse than in the low noise, as to be expected, because we are saving the noise of the instrument by switching around where the gain happens in the chains of the SR560 internally. But at some point, the low noise one hits the nonlinearity earlier. Now this is not a lot of difference at this particular gain, but this difference becomes worse and worse if the gain of the SR560 is higher. So you can see that over here, in the low noise version, you have a much worse performance, but over here in the dynamic range, you have a worse performance. As always, it's a compromise depending on the input and output range you're looking for. And these plots can be adjusted. You can change the title, you can put whatever you want and then save them and print them and so on, which is the point. So if you need to make a report of the device under test you're testing, you can use this. So now let's try and see if we can characterize a tiny audio amplifier board, which is sitting right over here. It runs from 5 volts and it's supposed to have 40 dB of gain. So the setup is really quite simple. The output of the DAC goes to the input of the amplifier, and the output of the amplifier goes back into the ADC. Now we're loading this amplifier with a 200 ohm load, which is not a very small load, but nonetheless is going to put some strain on the amplifier itself. If you look closely over here, you can see that it is a 2-stage op-amp in one package, and we're going to power the whole thing using the Roden Shores power supply there in the back. So right now the amplifier is not powered on, so we're basically just measuring the noise of the instrument itself. I'm going to apply the 5-volt power supply. Here we go. Now, as soon as we apply the power, we see some of the tones of the power lines again being amplified, but we also see a very clear shape of the noise. So as soon as I apply a signal, I expect to see the gain measurement. Let's go over here. We're going to apply a minus 40 dB volt signal at 1 kilohertz again. We're going to enable that. And as soon as we enable that, there it is. We see our signal over here. We do indeed have a gain of 40 dB, exactly what it should be, putting out 1 volt RMS from a 10 millivolt RMS input. And it is indeed quite nonlinear. As you were seeing, that all the different harmonics are showing up way above the noise floor here. And this is definitely coming from the op-amp. And the THD is minus 37 dB when it is providing 1 volt RMS. Not the greatest amplifier itself, but I am pushing it a little bit. But I want to characterize this frequency response. Now we can characterize it using the frequency response button over here, or we could use one of the built-in automated tests, which gives us quite a bit more detail. So here we go, let's use this one. Amplifier frequency response. We're going to use the minus 40 dB volt input going from 20 Hertz to 20 kilohertz. And we're going to let this thing run. And here's the response of the amplifier. A few interesting things to note. First of all, the input of the amplifier is AC coupled. So at very low frequencies, the gain drops as to be expected. And the gain reaches almost 40 dB just before this point around 1.5 kilohertz or so. And take a look, there is a big peaking in the middle of the band. This is typically undesired because if you put audio in here, you're going to get some of the frequencies amplified. Sometimes that may actually sound better depending on the equalization you want to apply. But this is not good. And this peaking in the middle of the bandpass of this amplifier may have some other consequences, especially on the linearity of the amplifier. So let's keep this in mind and now run a different test. This time I'm going to run a different test now using the THD as a function of frequency. So before we ran THD as a function of input and output level, but you can also run it as a function of frequency too. I'm going to let this thing run one more time. Now we're going to see if the THD is affected as a function of frequency and if that peaking is going to hurt us or not. And check out this result. The THD gets really bad right at the peaking level. And that's to be expected because at that point, the amplifier is going to produce the highest output because it has the highest gain, and therefore is going to experience the worst nonlinearity. So you can now see that these automated tests can be combined in many different ways and characterize your system. And this is why there are so many of them written here. But because it is a script-based system, they can just keep adding more and more into this list of already predefined programs, and you can of course write your own. So it's really quite useful to have these handy. And QuantAsylum also makes a bunch of other hardware aside from the QA403 we're seeing here, as well as things like loads and transducer drivers and low-noise preamplifiers. All of these are obviously intended for audio applications. And if you go under, for example, the QA403, there's a whole bunch of test examples for microphones, speakers, DACs, and LDOs, and even measuring noises of various components. And you can draw a lot of inspiration from how they set up their own setup examples and how they measure the various elements that are listed here. So it's really quite helpful, especially if you're just getting started. And there you have it. I hope you enjoyed this detailed look at the QuantAsylum QA403. Let me know what you think about it in the comment section. If you have any other questions, I'm sure the creators would also be happy to answer you. As always, thanks so much to the Patreon supporters. There's also a PayPal link if you want to support the channel. That way, you make all of this possible, and your support goes a very long way to making new videos. I'm working on some pretty cool stuff coming up in the future, so keep an eye out on the channel. I'll see you next time.